Well, hello, good evening. My name is Roger Siegel, and welcome to AP Physics Live, AP Physics C, Electricity and Magnetism. I'm coming to you tonight live from my home in Sarasota, Florida, where I teach AP Physics. And with me tonight, as always, is my friend and co-teacher, Kristen.
Hi guys, my name is Kristen Gonzalez Vega and I teach at Reedy High School in Frisco, Texas.
Okay, great. Well, as I said, we are doing AP Physics C tonight. If this is your first time with us, welcome. And we've been doing this for quite a while. For the past week and a half, we have been reviewing for the AP exam, and we're going to continue doing that. I'm going to share my screen with you guys, and here we have ready to go. Okay, so let me minimize this. We don't need to see that. And we'll come over here. Okay, great. So today, as I said, we are reviewing for the AP exam. The section that we're covering tonight is 2.1, Conductors, Capacitors, and Dielectrics. And tonight, we're focusing on dielectrics. And the dielectric, we're going to talk about what that is. All right. And again, my name is Roger Siegel here from Sarasota. I teach in Pineview, and Kristen comes to us from Frisco, Texas. Before we get started, I do want to remind you of your exam date and time, and that is going to be on May 11th, and depending on where you are, is going to dictate what time you're going to take the exam. So please make note of your times. Go ahead and put them in your calendars. Tell your parents, and make sure that you have a nice, quiet, and calm place where you're going to sit down and take the test. Do want to talk about what we're going to do what we're doing this week and what we've been doing. We started on Monday with the capacitors, and we did 2 days with capacitors. On Monday, we did parallel capacitors, and we looked at them in circuits and such. And then on Tuesday, we did spherical capacitors and cylindrical capacitors. And today, we're going to do dielectrics. All right, so our objective today is to describe or explain the physical properties of an insulating material when the insulator is placed in an external electric field. Explain how a dielectric inserted in between the plates of a capacitor will affect the properties of the capacitor, such as the potential difference, electric field between the plates, and charge on the capacitor. Use the definition of the capacitor to describe changes in the capacitance value when a dielectric is inserted between the plates. Calculate changes in energy, charge, or potential difference when a dielectric is inserted into an isolated charge capacitor and one that is connected to a source. So these were actually two different objectives. One said isolated and the other said connected, and so I just combined them into one. All right, we'll see these problems tonight, and hopefully, usually the objectives only make sense after you've seen everything, but we always want to lay it out for you. All right, so what we have here is, what is a dielectric and what does it do? Well, a dielectric is an insulating material that we put between the plates of a capacitor. So conceptually, it's something that goes like this in between the two plates. It can be, usually it could be paper, it could be glass, but we definitely don't want it to be a conductor. It has to be an insulator because we still want this to be a capacitor. Now, what does it do? Well, it increases the capacitance. That's what it does. And how does it do it? There's two ways. One way is it actually creates more ways or more places for energy to be stored, and that'll make sense in a minute. And the other way is it allows the plates to be brought very close together without touching. And think about it, we know that if we want the capacitance to increase, what we're going to do here is we're going to make the distance between them as small as possible. Well, how do you make the distance between two plates small as possible without having the plates touch? And the way you do that is by putting an insulating material between them. So those are two really important functions that the capacitor plays for us. We're going to see how that works out. Now, I want to remind you that our formula that we learned, I think 2 nights ago is when we first looked at it, is right here. And this formula has this K in it. And this is the dielectric constant. And on Monday, I said, and last night, Kristen and I said, that for the previous 2 nights, we've always considered this value to be 1. So much so we didn't even write it because we didn't have a dielectric. But today we're going to talk about what a dielectric is and how it works and how it changes the properties of the capacitor. So we're still going to have an area, we're still going to have a distance, and we'll still, we still have C is equal to Q over delta V. That doesn't change. But what does change is this value of the capacitance. All right, so let's talk about how the dielectric works to increase the storage capacity of a capacitor. So in the absence of an electric field from the plates, atoms in the dielectric are randomly oriented. So I want you to imagine that we have plates here. And these are, I haven't charged them up yet. So we're not hooked up to a battery. We just have plates. And so there's no electric field in here. So in the absence of the field, all of these atoms are randomly oriented, and they're just doing their atom thing. So that's what we kind of have here. Although I have to say, these atoms are already drawn as polarized. So I kind of don't like that. I kind of wish the atoms were just more like spheres with a nucleus in the middle and an electron cloud around it. So let's just imagine that we have that too. We've got these atoms that are right here. Now, as soon as I turn on the electric field, and I'm going to go ahead and take this over here, I'm going to put a positive battery here. As soon as I do that, look what happens. I start to push positive charges here, okay? And I start to get then negative charges here. All right, so let's go ahead and zoom in on that and see how that's going to play out. All right, so I've got this I've got this electric field E naught, and that is my electric field that I would have without a dielectric. Okay, now each one of these my little atoms has now been polarized, and it's been polarized by this electric field. What does that mean? Well, that means that the protons are going to be pushed in this direction toward the protons are going to be pushed down, and the electrons are going to be pulled up. And so that's just going to happen. We're going to get these little stretched out atoms. Now, each one of these atoms, once the electric field turns on, is going to get stretched out. And now what's going to happen is we're going to get, when we have a charge separation, look what we have here. We've got this E field that goes from positive to negative. So each little polarized atom creates an E field, a tiny little E field in the opposite direction. And so each atom contributes to this E field, and I'm going to do them all just because I'm in the mood. So we've got an E field from each atom. Tiny as it is, there's a lot of atoms, and so they all add up to an E field that is now induced in the other direction. And so what I've done then is I've reduced the total electric field in my system. I've made it smaller. All right. So that is how a dielectric. Okay, so let's one more thing. Sorry. So now I've made the electric field smaller. So let's go ahead and see what happens in this situation. We know that C is equal to Q over delta V. Okay. And so what has happened here is, since I'm hooked up to this battery, I've got the same delta V. That's not going to change, but my capacitance has gone up. As a matter of fact, it's gone up by a factor K, which means my charge has gone up. So now I can put more positive charges here, more negative charges here. And so I hope you can see that the capacitance, the capacity of my capacitor, goes up due to this induced polarization, creating a reverse electric field. All right, let's go ahead and talk about the dielectric constant of some different materials. I just added a table here that I like. So far, I said earlier that on Monday and Tuesday, we just didn't even write the K. We just considered it to be 1. We did cheat a little bit because air is a little bit more of a dielectric constant than vacuum. Not much, but a little bit more. So, but we usually just call it 1. There's nothing wrong with doing that. But then look at some of our other materials that you may be familiar with, you've heard of: Teflon, paraffin, polystyrene, silicon, silicon oil, glass, and you can see that these can get pretty high, these values. And so we can do some really great things with our capacitance. We can really increase the amount of energy that we're storing by using these capacitance, these dielectrics. Now, I want to pull you over to a simulation that is on PHET. And let me go ahead and reset this simulation. So I think it's pretty much better to start from scratch. And notice that what I have here is I've got a battery and a capacitor, and I'm able to move the capacitor in and out, the dielectric in and out of the capacitor. So I can have a capacitor with no dielectric, and then I can introduce it. And so let's talk about what can happen here. So first, I'm going to go ahead and put a charge on here, and I have a choice now. I've charged up my capacitor. I can either disconnect the battery and have a constant charge, or I can connect the battery and have a constant voltage. And that's going to determine how I proceed with my issues, how I deal with the problems. But watch what happens here. Let's leave the battery connected, and I'm going to have a constant voltage. Now, what did we just say about that? Well, we said that if we have the capacitance is equal to Q over delta V. All right. So if I leave the battery connected, that means my delta V is constant. If my capacitance goes up, my charge will go up. So let's go ahead and take a look at that. All right. And so I'm going to leave this connected, and you're going to see as my capacitance goes up, my charge goes up like that. More charge. That's a beautiful thing. Now, let me show you the other situation. What happens? Now, if I have if I disconnect the battery, then what I'm doing is I'm isolating the charge, and my voltage can change. So let's see what happens there. If the capacitance goes up by a factor of K, how do I make this side become more? Well, I can't change the charge, so I have to let the voltage get smaller. And so let me go ahead and bring back the simulation. I'm going to grab a voltmeter, and let's pretend that we're in our lab. I miss my lab. I'm sure you miss yours too. And so let's see, we have 1.5 volts. And so we know if the battery is connected, then we're always going to have 1.5 volts. But if I disconnect the battery, we said the voltage should go down. And indeed, we do see that. So that is a good simulation that helps us to move forward with what we're doing. I recommend that you visit the PHET simulations. They are a real wonderful thing for a physics teacher and for learning about physics principles and ideas. So that's what I've got for now. Those are the ideas that I want you to run with. We're going to throw it over to Kristen in Frisco. She'll do some problems with you, and then we'll do some more and close it out.
Okay, great. Thanks, Roger. It's so neat to see when you put that charge going up on those plates. So let's look at a couple of examples then, kind of with that same concept. And we did this with just our plain capacitors with no dielectrics the other day too, and looked to see if you disconnect it from a battery and we separated the plates, what happened with the charge and the potential difference and the energy. So we're going to do the same thing. We're not going to change the actual plates of the capacitor at all. We're going to just change that dielectric by adding it in. So we're going to do it once with the battery attached and then once without the battery. So if we have a parallel plate capacitor and it has a capacitance of C naught and plates area A, separation D, when it's connected to a battery of voltage V naught, it has a charge of Q naught on its plates. While it is connected to the battery, the space between the plates is filled with a material of dielectric constant 3. Okay, so we've got our plates here connected to our voltage and charge Q. The plates have an area of A. And so we're going to fill that in with our dielectric that has a K of 3. And so I want you to tell me what is going to happen to the charge on the plates, the capacitance of our capacitor, and the potential difference between our plates. It's going to be just a second to think about that, jot something down. Okay, so if we look at our capacitor, we have that equation that we've been talking about and discussing. So what are we going to change in our equation? Well, I'm not changing the surface area of the plates of my capacitor. I'm not changing the separation distance of the capacitor. All I'm doing is inserting that dielectric that has a K of 3. So how's that going to change the capacitance of the capacitor? Well, if we have the top there multiplied by 3, then the capacitance is going to be multiplied by 3. Okay, what about the charge? How can we relate the charge? And what's going to stay the same? If it's connected to the battery, still, what should stay the same? That voltage drop. So our V is going to be equal to V naught, or 1 times V naught. And then if we want to relate the charge, and we know that V is equal to Q over C, or C is Q over V. If V is staying the same, if C is 3 times as much, what has to happen to Q? It's got to be 3 times as much. Okay, now let's look at the energy. What's going to happen to the energy that we've stored on here? So remember, we had a few different equations that we could use for capacitance. So one of them was that U is equal to 1/2 Q delta V. So I like to pick this one because delta V is not changing. And if we have 3 times the charge, then we're going to have 3 times the amount of energy. So U is going to be equal to 3 times the initial energy stored in that capacitor. Okay, and then we have this last question on here. To insert this dielectric in between these plates, did we have to give it a push or is it pulled in, right? So is this something that you are going to have to do work to put into there, or is it going to be pulled in by that electric field? So how do we know? What we want to look at is we want to look at that change in energy. Is the energy increasing or decreasing? And so here we had an increase in energy. Well, how do we add energy into the system? We've got to do work to put energy into the system by that external force, right? There's got to be an external force acting on that system to increase the amount of energy that it has. So if we had to do work on it, then we had to give it a push. Okay. And then if we look at the next one here, we're going to do the same thing, except this time we're going to disconnect it from the battery once we charge it up, right? So same plates, charged up to the same potential difference initially. Charge the same, A the same, capacitance the same, except now we're going to disconnect. Once it's charged up, we're going to disconnect it. So let's open up a switch here in our circuit. And then I'm going to, again, fill it with the dielectric, same dielectric. So I'll give you a second again. What's going to happen to the charge now? The capacitance and the potential difference across the capacitor. So if we've got the same situation, then the same thing's going to happen to our capacitance, right? We're defined by that dielectric constant K of 3, but everything else is staying the same in the situation. So our capacitance is still going to be 3 times the original capacitance. But this time, our potential difference is not going to be the same. This time, if I open up this switch, now what has to remain the same? Well, the charge on the plates has to be conserved, so Q is going to be the same. And so again, if we go back to that V is equal to Q over C, and Q is staying the same, well, if C is 3 times as much, that means our potential difference actually went down. You can store the same amount of charge for a lower voltage on your capacitor. Okay. And then did our energy increase or decrease? So for this one, since charge is staying the same, I'm going to use that U is equal to 1/2 still Q delta V. And so if our charge is staying the same this time, but my potential difference went down by 3, that means my energy is now 1/3 of what the original energy is. So now our energy is decreasing. So if that potential energy stored on our plates is decreasing, what does that mean? That means this time that that dielectric is being pulled in as we're decreasing that energy. Right, so there's a couple of situations there that we can look at with those plates. And now we're going to give it back to Roger, and he is going to take us back to our spherical and cylindrical capacitor and what happens if we put a dielectric into those ones.
All right. Well, let's take a look at those. Thank you, Kristen. Let me get you my screen back and let's take a look at where we are. Okay, there we go. All right, so now we're going to do a couple of really interesting problems. And I love these. I like to pretend maybe I could have been an electrical engineer, somebody designing amazing capacitors and things like that. So let's see what we can figure out. Maybe there's some future electrical engineers in the audience. Maybe you guys will design incredible capacitors and batteries of the future. But let's take a look at it. So we've got a conducting sphere of radius A. You've seen this guy before. Charge Q surrounded by concentric conducting shell of inner radius B and outer radius C is shown. The outer shell is first grounded, then the grounding wire is removed. Using Gauss's law, determine the electric field in the region. Okay, and so between A and B. Well, we know that when we want to find the electric field here, we're going to draw a Gaussian surface around this region. And we know we've done this many, many times that this is E dot dr, dA, sorry, vectors, is equal to the enclosed charge over epsilon naught. And I have to tell you, I know that at this point, you guys have been tuned in the whole time. You've seen me do this or Kristen do this, I think every night for a week. So I'm just going to relieve us of that burden. And I'm going to say that E is equal to KQ over R squared, remembering that that's what we get when we have a spherically symmetric charge and we put a Gaussian sphere around it. Okay, it's a point charge. It behaves like a point charge. So that's our E field. And we want to find the capacitance. So this is a review of what we did last night, because we know that the capacitance is equal to Q over delta V. And so this is a good practice. I don't think we've done this one nearly as much as we've done the Gauss's law one. And this is a big deal. This is important. So let's go ahead and do it. We're going to find delta V. Well, we know that delta V is equal to the integral of negative E dot dr. And remember, the convention when we're doing a potential difference is to start at infinity and to leave your way in. So that means we're going from B to A. Even though with Gauss's law, we were kind of going the other way, usually with potential, we usually start at infinity. And so we're going to go from B to A. And so this is going to be the negative integral of KQ over R squared dr from B to A. And I know that you guys know your calculus really well. What that gives me is actually a positive from B to A of KQ over R. The 2 goes away, a negative comes out. And so, I'm sorry, let me go ahead and get rid of my integral sign. There we go. And so that's going to go from B to A. And so we have KQ times 1 over B. Oops, try that again. 1 over A minus 1 over B. And so that is our potential difference from going from B to A. And so that means that our capacitance is Q over delta V, or Q over KQ, quantity 1 over A minus 1 over B. And we'll just leave it at 1 over KQ, 1 over A minus 1 over B. I think that's okay. Now,
Hey, Roger, it just
yeah,
might be me. I can't see your sharing. Are you sharing or is it just me?
that would be a bad thing. I think I'm not sharing. Oh my goodness. Thank you so much for telling me I wasn't sharing.
Yes.
Thank you so much. Okay. I am sorry, ladies and gentlemen, that you just had to hear me and look at the top of my head as I was looking down at my tablet. It's a beautiful head, I know, but it's okay. Let's go ahead and take a step back and see what I've been talking about. So I'm just going to jump in here and pick up where we left off. Okay, so this is our conducting sphere of radius A and charge Q, and we've seen this one before, and we've seen it so many times that I'm going to give us that the electric field between A and B, if you remember, we've got a spherically symmetric charge surrounded by a spherical Gaussian surface, that's KQ over R squared. And so down here, if we want to find the capacitance of that, we have to say that C is equal to Q over delta V. We have to find delta V. Well, we know that delta V is equal to the negative integral of E dot dr. And so that's going to be going from B to A. And just real quick, why do we go from B to A? Well, the reason we go from B to A is, in general, when we're finding the potential, we start at infinity at 0 and we go in from there. And so the first place we would get to there would be B. All right, so let's go ahead and see what we have next. So we're going to find the potential difference. When we take the integral of this, what we get is the negative integral from B to A of KQ over R squared dr. And so that becomes, when I take the integral of E of a number to the -2, it's in the denominator, what we're going to get is KQ over R going from B to A, or that's going to be KQ 1 over A minus 1 over B. And so that's how we get our potential difference. And so now we can find the capacitance, because we know that C is equal to Q over delta V. And so that's going to be Q over KQ quantity 1 over A minus 1 over B. And so that's going to be 1 over K quantity 1 over A minus 1 over B. And now we're caught up. Okay, now the next one says, look what happens. It says a liquid dielectric with a dielectric consisting of 4 is inserted in the space between the conducting plates and shell, filling half the space shown. Determine the capacitance C of the system in terms of C naught. Now, the first thing we got to ask is, okay, I've got 2 capacitors here. I've got one with a dielectric, one without. So the question is are they in series or are they in parallel? So let's go ahead and give that a shot and see whether they are. So I'm going to draw over here a parallel plate capacitor, and then I'm going to draw I'm going to fill half of it with a dielectric, but then I'm going to draw the same capacitor, but now I'm going to fill this half with the dielectric. Now, check it out over here. Look at every E field. It's got to go through both the dielectric and the no dielectric. So when I analyze this, this is behaving like 2 capacitors in series. As a matter of fact, I got to write it differently. Say it's behaving like 2 capacitors in series. This one over here, let's zoom in on this. Now this one over here, let's check out the E field here. It goes through this part, but then also through this part. So there are these two capacitors that share plates. And so this is equivalent to two capacitors in parallel. So before we ask what the capacitance is of our combination, we've got to decide, are they in series or parallel? I'm so grateful that I know that now. So let's go ahead and take a look at it and see what's going on. So let me zoom out again. So now we've got this shell, and you notice I'm going to have electric field, and my electric field is going to go this way through some dielectric, and then one through with dielectric. And to me, that looks like parallel. Okay, and so what we have are two parallel capacitors, and let's talk about how much capacitance each one has. Okay, now the first one over here has the capacitance C0, but let's think about that. For a parallel plate capacitor, and I can generalize this in this problem to a spherical capacitor, we know that C is equal to epsilon naught A over D. Well, here you can see I only have 1/2 of the area, so I only have 1/2 of the capacitance, and that's this part, my C0. Now, my new capacitance here is going to be 1/2 of C0, but it's also multiplied by 4. So that's going to be 2 C0, and this is going to be 1/2 C0. And if you remember, when we have capacitors in parallel, the sum, the capacitor in parallel is the sum of all the capacitors, one going from 1 to n. So I just add them up. And so this is 1/2 C0 plus 2 C0, and that's going to be 5/2 C0. Look at that. And so, just to I did that kind of fast, so let me come back and show you how I decided to do that. So we first asked the question, are these capacitors, is this capacitor where it's got a dielectric on the bottom and no dielectric on the top, it acts like two capacitors, but does it act like two capacitors in series or in parallel? And so we asked the question, well, is it like this with the dielectric on one part, or is it like this with the dielectric on all the parts? And it's in just one part, and so we decided that that was parallel. And so we had to add two capacitors that are in parallel, and the C0 was before I put the dielectric in. So now this is 1/2 C0 because it has no dielectric. This is also 1/2 C0 times 4 because it's now 4 times the capacitance. And so we got 2 plus 1/2 gave us 5/2. All right, that's a good one. I did that twice for you. Now let's do the last one tonight. And lo and behold, we might get out here early. Okay, so let me work through this one. We've got, again, the cylindrical capacitor, and it's a coaxial capacitor. It's got the cylinder of radii A and B and the length L and the capacitance C0. So right now, this capacitance is C0, okay? And so we have now 1/3 of the length of the capacitor is filled with a dielectric of dielectric constant K equal 2 is shown. What is the new capacitance in terms of C0? I'm going to do the same thing I did before. Let's try and figure out what is the situation I have going on. All right, so I'm going to go ahead and start with just the parallel plate capacitor. And I'm going to ask myself, when I'm inserting half of it with a dielectric, or a fraction of it with a dielectric, in this case 1/3, am I putting 1/3 here and leaving 2/3 empty? Or, and this one's a little bit tougher, let me zoom in over here, that'll help a little bit. Or am I doing 1/3, let me do it in blue, am I doing 1/3 here? 1/3 of D, that's the question. Okay, that's what we have to figure out. Now, in this case, you can see that the E field, if I have it, if I draw it, it's going through some places, it does go through the dielectric, but not everywhere. And if I look over here and I draw my E field, this is going through the dielectric everywhere, which means that it's acting like two separate capacitors, one with a dielectric, this would be 2/3 of the distance, but the dielectric is in this one. All right. And so that's what this would behave like. Over here, look at what we have. We've got two capacitors. Okay. And I haven't changed the distance between them. I don't have 1/3 D and 2/3 D. But I have changed the area of each one. This is 1/3 of the area here. And over here, we have 2/3 of the area, 2/3. And this is my part with the dielectric. So these two are in parallel. So once again, our example that we use is a parallel example like the previous one. I'm sure if we dug and we looked through the textbooks, we would find a series example, but I don't have one for us tonight. All right, so let's go ahead though and do this one and see if we can figure out what's happening and what we can do. So once again, I'm going to remind us, again, this is for a parallel plate capacitor, but we're going to generalize it to this form because we can, and it'll work out fine. So I'm going to go ahead and say that C is equal to epsilon naught A over D. All right. And so let's see what we have here. So this is C naught. All right. Now we have two different capacitors, and let's see how we've changed them. So instead of this one being an area of, this was, equal to epsilon A over D, since we have 1/3 of the length, we also have 1/3 of the area, 2/3 of the length, we have 2/3 of the area. So this is going to be 2/3 of C naught. Okay. So that's, let me write that over here actually. These are my two capacitors. I'm going to finish drawing them. There's my two capacitors. And so this one is 2/3 C naught because it's 2/3 the area with no change in dielectric. Over here, this one is 1/3 of the area C naught, but then look at that, there's a K, and that K is times 2. So I've got 1/3 the area twice, which gives me 2/3. Now, since these are in parallel, I add 2/3 C naught to over here 2/3 C naught, and I get 4/3 C naught. Isn't that beautiful? So that is how we add electrolytes to strangely, did I say electrolytes again? Oh, I don't even teach chemistry. That is how we add dielectrics to strangely shaped capacitors, be they cylinders or be they spheres or be they parallel plates. Okay. I do want to just tell you once again, just a little bit of help. Remember that we have Coulomb's law in our magic square. That's K Q1 Q2 over R squared. Here we have energy. This is U is equal to K Q1 Q2 over R. Notice we divided out, we multiplied out an R. It's a vector. Here we have the electric field. We divide out one of our Q's. That's going to be KQ over R squared. And then over here we have our voltage, which is equal to KQ dividing out one of our Q's over R. Knowing the units is so helpful. These are newtons. These are newtons per Coulomb because I divided out the Q. Now, when I go over this way and I multiply by meters, I get newtons times meters, which we know is joules. However, when I divide by Q coming down here, volts is joules per Coulomb. And then one last one, electric field is also, look at now, I'm going to divide volts per meter. I promise you, knowing those things is going to save you on a problem someday. All right, that's all I got for you. This has been a wonderful time. It's so good to work with you guys each night and to get to share what we love most, which is teaching physics. Kristen, did the storms come through in Frisco?
No, it got really dark and windy, but not a drop, and now it's sunny again. So
Okay. I want to tell you, I did all the problems tonight in case you were going to be shut down. So even the ones you were going to do, I prepped them so I was going to be ready. All
you're
right.
all
Well,
good.
that's all we have for you tonight, this Wednesday night. Remember tomorrow, what's really exciting. Tomorrow we're going to start circuits, and I love solving circuits. I think you will too. We're going to repeat a lot of the things that you've seen maybe in an earlier physics class, but we're also going to remember, we're going to do some calculus, and it's going to be amazing. So from Sarasota, Florida, and for AP, thank you for joining in, and join us tomorrow night, same time, same channel.